So now let's look at the last part of the thin film deposition. This is the summary of the thin film deposition. For example, for the epitaxial silicon, we use APCVD. Sometimes we use low pressure CVD. This is done at high temperature. The high temperature gives you epitaxial film. For the polysilicon, we use LPCVD and nitride, LPCVD, PCVD, and etc. And now we will look at those processes one by one. The first one is the epitaxial silicon deposition. This one we use APCVD method. So this offers why we need epitaxial wafers. This offers the means of controlling the doping profile. For example, we can have lightly doped silicon on top of heavily doped silicon, and also epitaxial layers are general. There is no oxygen and carbon in the epitaxial layers. This is for the APCVD, so we can use this kind of chamber, and we can also use the furnace. For this one, as you can see here, so we have this RF coil. So here, this is the RF coil. So we have this is the induction heating. So when we have the induction heating, this one is the cold. It is cold wall. And this you can put the many wafers like this, and the gas flow is like this. But now my question is, so why it is like this? Why there is a slope, not vertical? So why there is a slope here? Why there is a slope? So this is similar to what we have seen in the first slide site. Here, so this you can see here. So when you put the wafer, you have the slope. You have a slope like this. And also you look at the cold wall and hot wall at the beginning. So this is the cold wall. So this is the cold wall, and this is the hot wall. So for the cold wall, so we have a slope. When we put the wafer, we put it on the slope. So in the past, in the early time, the main gas we use is this one, silicon tetrachloride. So later on, it shifted to this one. Now those two gases are popular for the APCVD silicon deposition. Sometimes, but this is not so often. Those are the most popular. So this is the basic process. So first, we have hydrogen gas poured over the chamber, then heat to high temperature. At the thermal equilibrium, we use HCl gas to etch the chamber. This is to clean. To etch away the material. For example, when the HCl can etch away the silicon to form silicon dichloride, can form the this is called the dichloride silane. So this can etch away the silicon, and it can also etch away the metal. So we know the metal is not good for the silicon. So HCl can etch away the metal in the chamber. Then the temperature is reduced to the gross temperature, and we have the source material and the dopant introduced into the chamber. Then we have the gross. Then we cool down, we reduce the temperature and shut off the power. Then we use hydrogen flow to replace the nitrogen. Hydrogen flow replaced by the nitrogen flow. So normally we can do 10 to 50 wafers per batch. Because here we can put 10 to 50 wafers per batch. For the LPCVD, we know for the LPCVD, we can put more than 100 wafers. Because for the LPCVD, we have the wafer we put on a stack like this. So the process time is about 1 hour. So normally for the epitaxial film, because this is a single crystal film, epitaxial means single crystal. So single crystal film, we need high temperature so that the film can go to equilibrium state. That gives you the single crystal film. And also at high temperature, it can remove the native oxide. So this native oxide will be dissolved from the surface. This one we get a fresh single crystal silicon lattice for the epitaxy. So normally epitaxial film we need to run at the mass transfer limited regime. So for the mass transfer limited regime, we have to put the wafer like this. We cannot put the wafer vertically. We have to put the wafer like this. And this is because this is why we know that mass transfer limited regime has lower throughput. You can put 10 to 50 like this. This is why we can go to 100 or 200 wafers. The lower throughput, we have fewer wafers that can be deposited each run. So why we need to run at the mass transfer limited regime? So because For the reaction limited regime, the growth rate depends on the crystal orientation. As a result, we have some crystalline defect, then it will become larger and larger, then it may have very rough film, it may get very rough film surface. But for the mass transport limited regime, for this one, mass transfer limited regime, as long as the gas comes to the wafer evenly, you get even deposition. So there will be no bump because of the crystalline defect. Now let's look at a polysilicon deposition. So polysilicon is used for the gate of the MOSFET, but today we use this one. So metal gate, high K material, and coupled with the metal gate. No longer use the gate no longer use polysilicon for the gate material. We usually deposited using LPC low pressure CVD because this one, as I said, gives you high throughput. So we can put many wafers at the same time. The deposition at 600 degrees and 10 to 20 nanometer per minute. So we use silane gas. The silane gas gives lower deposition temperature, as you can see here. So this is the silane for the same deposition rate. This is the deposition rate. For the same rate, we will look at here. So silane gas, we need a temperature like 600 below 700 degrees. If we use other gases, we need a higher temperature. So here deposition rate. At the low pressure, the rate goes up, then become saturated because then it goes to the chemical reaction limited regime. So you can see higher temperature gives you polycrystal film, lower temperature like this, and this is the amorphous. So usually at the temperature less than 575 degrees, we got amorphous film. But if we deposit, if temperature rate is very low, then we can get polycrystal. You can see. So when we have low temperature rate, we got polycrystal film. So we get columnar green structures and textures, and the green will grow when annealed. So when annealed, the amorphous silicon will become polycrystal silicon with larger green size, and then the polysilicon and the same annealing. Now let's look at silicon nitride. So for the silicon nitride, so we always use LPCVD or plasma enhanced CVD or low pressure CVD. So in this class, so we use silicon nitride to prevent oxidation, and also is the preservation layer to prevent moisture and the sodium from getting into the wafer. It's also used as an etch stop for the copper damascene process. So this one is for the interconnection. So we use silane gas and ammonium gas, and we can also use dichlorosilane or ammonium. At the University of Waterloo, so we have this one. So we have this one for the LPCVD at the University of Waterloo, and we have this one for the PCVD. So here is the property comparison of the film deposited by two low pressure CVD and plasma enhanced CVD. This one is higher temperature. So normally you can see that higher temperature gives you better film quality. So you can see the combination can be well controlled. The ratio is correct. Silicon nitride ratio is correct, but not so much hydrogen. So this PCVD, you have a lot more hydrogen. We have a constant, stable refractive index, and high density, high resistivity, and high dielectric strength, and energy gap is about 5 electron volts. So the stress can be tensile or tensile stress, but it can be 0. So this is called a low stress. So low stress silicon nitride is very important for the MEMS, micro electromechanical system. So we often need low stress silicon nitride. So you can make the silicon rich, That means we have this gas very high and this gas very low. So we get silicon rich deposition. Then we get a low stress. So the deposition can be very conformal because the same thickness along everywhere. But for the silicon oxide deposition, so we also use LPCVD most often we use low pressure CVD, but it can be done by using silane and oxygen at a pretty low temperature. But this one we have it here at the University of Waterloo. We can also use a TOS based LPCVD or PCVD. So here we have PCVD based on TOS, TEOS at the quantum nanofab clean room here. So this is TEOS. TEOS is the tetraisoxysilane. So this is the tetra, so 4 tetraisoxysilane. You decompose to form the silicon oxide. So this will give you more conformal deposition because it has a lower staking coefficient. But that means when the silicon comes to the surface, or if the OC2H5, so this will come to the surface, it can move around. But when it moves around, or it can be bounced back. This means low staking coefficient. Then give you more conformal deposition. For the PCVD, we can use silane and N2O. We can also use the dichlorosilane and N2O or TEOS plus ozone. Here's the comparison of the different oxide film, silicon oxide film, by different methods. So we have the thermal oxidation. This is the we talk about thermal oxidation in chapter 6. Then we have low pressure CVD, dichlorosilane gas, low pressure CVD, TEOS, and the low pressure CVD, silane, and the PCVD. You can see oxidation gives the highest temperature. So this is the combination. This one is very pure. Thermal stability, rigidity is the same. Stress, we have stress. Dielectric stress, you can see so thermal oxides give the highest dielectric stress. So the action rate, this one is slowest. So we have slower action rate. It means better. The action is done by the HF, by the hydrofluoric acid. The lower action rate means better film quality, denser film. So this is the thermal oxide is very dense, but this is why you can see it's much higher action rate than thermal oxide. So this film quality is not as good. And those are the conformal. But this is the TEOS that we have seen. But this one is conformal. But this one silane oxygen, but this is not conformal. But this process is called LTO, low temperature oxide. So we have LTO here in campus. And now let's look at metal deposition. So for the metal, normally we use magnetron sputter deposition. Magnetron gives you faster deposition rate than normal sputter. The same for the titanium. The tungsten we use a CVD. We use low pressure CVD. And we have the WF6 and the silane to form tungsten. Or we can also use hydrogen to form the tungsten. So titanium nitride, so we use reactive sputter deposition. That means the target. So the target material is titanium, but we add nitrogen into the argon. So we have argon, we also add some nitrogen in the plasma, and we form the titanium nitride. So this is called reactive sputter because we have the chemical reaction here. So now let's look at atomic layer deposition. So for the normal CVD, for the CVD, so we have something like this, for example, A plus B to form the C. So the chemistry for the atomic layer deposition is similar to the CVD, except that the reaction is break the CVD reaction into two half reactions. So we have precursor gas A, introduced into the chamber, then it's pumped away. Then we have a second precursor gas B introduced into the chamber, then we pump away. So then we have this film formation, something like this. So we have precursor gas A introduced into the chamber to form a monolayer. Then it pumped away. Then we introduce a reaction gas B into the chamber, the gas B into the chamber, then pump away. But then A and B, there will be chemical reaction to form the film. So this is the monolayer. So each time we form one layer, so there's one layer of the film each of the cycle. So the film growth is self-limited. We have monolayer absorption reaction each half cycle. As a result, we can have atomic layer thickness control. So we can control the thickness very, very precisely because we can count the number of the deposited cycles to give precisely controlled film. This one was introduced in 1974 by the Finland scientist. But today, so we use ALD to do the high K materials. For example, we can deposit the hafnium oxide. This is the high K material. by atomic layer deposition. So here in campus, we have ALD. I can show you. So we have the atomic layer deposition. Here in this case, ALD and the PCVD is the same, is the cluster deposition. So one chamber for ALD, another chamber for the PCVD. So we have also low pressure CVD, low temperature oxide. So low pressure CVD, polysilicon and silicon carbide, and the LPCVD and silicon nitride. So this is the ALD. So ALD we can deposit aluminum oxide, titanium oxide, and hafnium oxide. But here we have the plasma. So we introduce the gas, and also we have the plasma to make the chemical reaction easier. But this we don't have to use plasma. A plasma may give you a better film quality. So if we want to see more, this is the quantum nanofab. You can see what equipment we have here. If we want to see more. Here, look at the example of the aluminum oxide deposition. So first, we use this gas. So we use this it's called TMA, trimethyl aluminum. So this is the trimethyl aluminum. And also we use water vapor for the chemical reaction. So first, we introduce TMA, trimethyl aluminum. So this one, we have hydroxyl group here. So this one and this one. So the hydrogen and this methyl group will go away to form the CH4, to form this methane gas. So then this one is gone. This one hydrogen is also gone. So aluminum gets linked to this oxygen. You can see aluminum gets linked to this oxygen. You still have this methyl group. Then we introduce the water. So the water we know is HOH. The water is HOH. But this H will react with this methyl group, and then another H will react another HOH. Another water molecule will react with the other methyl group. In the end, this is also gone, and this one is also gone to form the methane gas. So in the end, we have this OH group. This OH group is left over. You can see. So we have this OH group. Now you can see this is OH group, and at the very beginning, it is also OH group. So we have one cycle. Then it will keep going. You can have the film. So this is called the temporal ALD. Temporal. So we have the time. We have the a precursor gas 1 purge, a precursor gas 2 purge, a precursor gas 1, and etc. This is called temporal ALD. So we have the different precursor 2 and precursor 1. We need a high-speed valve, and also we need high-speed pump. This is the ALD process. Another one called a spatial ALD. At the University of Waterloo, so we have Professor Kelvin. So he is a professor of the mechanical and mechatronic engineering. So his group mainly work on the spatial ALD. In the spatial ALD, so we have the gas, inert gas precursor 1, inert gas precursor 2. So this can be argon. So we have the wafer. So we have the wafer move around. We have the wafer move from here to here, then move back. This way we can have much higher deposition rate because we do not need to turn on the valve or turn off the valve. Then you just move the wafer fast. You move the wafer fast below the different gases. Then we can have up to 100 times faster deposition rate. But this is the property of the atomic layer deposition. So you can see first the deposition rate is very, very slow. So we have very, very slow deposition rate. But its snap coverage is the best. We can have 3D conformal deposition. That means, for example, if we have a hole here, very, very deep hole. Yeah, a very deep hole. If we do the ALD, the coating will be pretty uniform. It will coat everywhere at the same thickness. If we use a PVD, physical vapor deposition, so probably the top part will be well coated, not much coating inside the hole. So this one gives you the best conformal deposition, a precise thickness control, and we have lower temperature deposition rate because we got only very modern layer per cycle, very, very slow. So we have very slow deposition. it can be done, it can be completed at low temperature. Deposition is gentle. The problem is slow deposition rate, and the materials that can be coated by the CVD is not many. But even though the deposition rate, the rate is slow, but we can have high throughput. We can have high throughput deposition by ALD because we can put the wafer like this. So we can put 100 wafers to get deposited at the same time. As a result, it is a low cost. It is a low cost deposition method because we can have so many wafers deposited at the same time. But for this one, I think you have to put the wafer like this. So you cannot put the wafer. You cannot put the wafer like this. It has to be horizontal. This one have lower throughput but higher deposition rate. So now let's look at a pulsed laser deposition. In this case, so we have the excimer laser like China chloride. But this is the same excimer laser as we learned in chapter 5 for the photolithography. But this can be China chloride or krypton fluoride. So this excimer laser shine on the target, then target gets ablated and gets deposited onto the substrate. So it gets ablated. I think the word is called ablated. The target material gets ablated, then gets deposited onto the substrate material. So we can also do two target co-deposition. One target here. We have the co-deposition. So we can reproduce the combination of the target. First response, you shine the laser, your deposition. Turn off the laser, no deposition. So flexible, easy to work with. So the atoms arrive in bunches. So atoms arrive from here in bunches. Then we have uneven coverage, a lot of defect and particulate concentration, and not well suited for the large scale deposition. Because if the wafer is very big, the laser beam here, so the beam here is small, so the wafer cannot be too big because the beam here is too tiny. So this is not very good for the production. At University of Waterloo, so we have this one at Water Lab. Chemistry, Water Lab, we have this machine. But the clean room, we do not have PLD in the clean room. Here, what happens? So we have the laser beam shine on the wafer, shine on the target. Sorry. So first we have absorption of the light, and we have the heating. They get melted and become the flow. They get vaporized. So then it got vaporized. So we have the vaporized because the energy is very energetic. So this vapor with the light, then it will cause the plasma. The vapor and the light, they call the plasma. Then the plasma can detach. The plasma can be detached from surface. You can see this is the plasma detached from surface. It's called a plume. Then it comes to the substrate for the deposition. So here this is the excimer laser. So all you need is a chamber. You need a high vacuum chamber. And you have the excimer laser shine onto the chamber. So this is another system. So those are the materials that can be deposited by the pulsed laser deposition method, like high temperature superconducting materials like YBCO, ferroelectric materials like PJT, ferromagnetism, electrochromic material. And this can be used for the color change. With these materials will change the color when you pass the current. So we have the electro-optical effect materials, piezoelectric material like this one. So this is called PJT. So PJT is one of the most popular piezoelectric material. So this one is also a PJT. It's also a ferroelectric material. GMR, giant magnetoresistance, like this one, thermal corrosive stability material. Wear, friction and wear, like this is for the like lubricant. This is like a lubricant. Silicon carbide and diamond like carbon. This for the wear resistant. So molybdenum disulfide is the low friction, like a lubricant. So biocompatible materials like this. Now we look at epitaxy. So what is epitaxy? Epitaxy refers to the method of depositing a monocrystalline film on another monocrystalline substrate. For example, we deposit this film onto this substrate. This is single crystal. The substrate is also a single crystal. There are two types. One is called autoepitaxy, another one is called heteroepitaxy. This one is also called homoepitaxy. So for this one, it is the extension of the substrate material, substrate lattice, by the overgrowth of the layer of identical material. For example, we have grow silicon on top of silicon. But then you may ask, what's the point? So what's the point to grow silicon on top of the silicon? So this one can be doped. So the doping condition, this layer can be different from the substrate layer. Then we have very well controlled doping by this epitaxial process. For the whole heteroepitaxy, for example, so we can grow gallium arsenide on silicon, or we can grow silicon on sapphire. But this one has lots of defects. Crystalline, we have lots of crystalline defects because of the mismatch of the lattice, So here is this one is the lattice match. So when we have the lattice match, so we grow the film, so no problem. But when we have mismatch, for example, this one is bigger than this one, then it becomes a strained. You can see it got elongated along this direction. So we have this called a strained film. The third way is the relaxed film. In this case, they do not match. The matching is not very good. The lattice match is not very good. But in this case, it got relaxed. Then we have this defect. So we got lots of defects. This is one defect here. We got one defect here and another defect here. We have defect when we get relaxed. Now this one is the superlattice. So what is superlattice? This is a superlattice. The superlattice is the repeated regular alternation between two monocrystal films. Two monocrystalline film. For example, here we have the silicon germanium alloy and silicon. So we have silicon germanium. So we have repeated. So this is called a superlattice. So this superlattice can give you the property you want. For example, this is widely used for the light emitting diode, and it's also used for the laser and photo detector. So this is popular. So superlattice is widely used for the light emitting diode or lasers. So because each layer is very thin, each layer is maybe 10 or 30 nanometer, then the mismatch, the lattice mismatch can be accommodated by the uniform strain. For example, here we have this, the constant is A2, this one is A1. So when they come together, you form this one, the B. So B is between the lattice constant of this one A2 and the lattice constant of A1. It's between A1 and A2. You form the film. You can see the A1. So A1 is bigger, so get shrunk laterally. For the A2 is elongated. So A2 is smaller, so get extended. This one A2 got extended, A1 got shrink along the lattice, and this one got elongated along the y direction. And there are three types of the epitaxial deposition. First one is the vapor phase epitaxy. Second one is the molecular beam epitaxy. This one is the form of the chemical vapor deposition. This one is form of the physical vapor deposition. So no chemical reaction. So the third one is the liquid phase epitaxy. For example, if we want to grow gallium arsenide, how to do that? We can do the liquid phase epitaxy. So what do we have? So we have arsenide saturated solution of gallium. So that means actually it should be, so we have gallium arsenide that is melted. So gallium arsenide is melted at over 1000 degrees. So gallium is melted at about 30 degrees. So gallium melted at 30 degrees. So gallium arsenide is melted over 1000 degrees. So normally, we write it this way. We write gallium arsenide, not arsenide gallium. So we write it this way. At about 800 degree, the sampling of the gallium arsenide, some of the percentage, maybe a few percent. So few percent of gallium arsenide can be soluble in the gallium at 800 degree. Then we cool down the temperature. We cool down the arsenic saturated solution of the gallium causes the arsenic to precipitate into the form of the gallium arsenide. So if we have the wafer here and you cool down, then the arsenide will come to the wafer. For the deposition. It forms the film. So the rate is about 0.1 to 1 micrometer per minute. So this is not very fast. So because we have limited arsenide, so in the end, the film is not very even. So you can imagine if this is the wafer here. There will be more deposition on the edge, maybe the film. You can imagine. So more deposition on the edge, then deposition on the center. Because you have more arsenide arrival on the edge than on the center. So this one, the deposition rate is limited, but arrival of this arsenide. This is the liquid phase epitaxy. So this is a cheap way. We do not need any machine. We just need a container. It will be done. Now let's look at organometallic process. This is called MOCVD. So this one is the most popularly used. For example, now we use the LED light bulb. The LED light bulb is based on the gallium nitride. So gallium nitride is grown by this MOCVD method. I know about 10 years ago, so 80% of the MOCVD were sold to China. Because China made the most of the LED lightning bulb. It's done by the MOCVD. So what is MO? Metal organic. We can see the source material here. So this is the trimethyl aluminum, trimethyl gallium. This is the metal and organic. That's why it's called metal organic CVD. Another way to call it is called organometallic vapor phase epitaxy. So this is another name. For example, if we want to deposit gallium arsenide, so what do you use? So you use this trimethyl aluminum plus arsen gas to give you this gallium arsenide. For the gallium nitride, so you use trimethyl aluminum plus ammonium gas to grow a gallium nitride. So this is the chamber. This is the chamber for the MOCVD. So you put the wafer like this. Side by side. But this one is also mass transfer limited. It's also mass transfer limited, so you put it on side by side like this. So why we need the mass transfer limited? For this same reason as we have seen before. I will remember here. So if we look at here, so epitaxial film generally needs to be run at the mass transfer limited regime, because otherwise, for the reaction limited regime, so so the growth rate will depend on the crystal orientation. There's some crystalline defect will give you very rough film. As a result, so we run at the mass transfer limited regime. So we put the wafer side by side like this. So beside the chamber, we can also do the MOCVD process using the chamber as we've seen before, using the cold wall chamber. So we can also do this one. We can also use this one. We can also use this top one. This is the cold wall, atmosphere pressure cold wall PCVD. Cold wall CVD for the MOCVD process. So normally the pressure is not, it is close to atmosphere pressure, but not always. It is about 0.1 to 1 atmosphere. So this is why we know for the low pressure CVD, its number is about 0.001 atmosphere. For the LPCVD, it's 0.001 atmosphere. For this one, for the MOCVD, it's 0.1 to 1 atmosphere. But this one is run as the mass transfer limited regime. So we can also, you can see here, so this one is the RF coil, so this is the cold wall. as we have just seen. So this we use the coil, for the heating, and you put the wafer, like this. So we have this. Those are the precursor gases. So we have this trimethyl aluminum, trimethyl gallium. This is the diethyl zinc. So this is for the zinc. So we have zinc selenide. This is semiconductor. This is the group 2 and group 4. So group 2 and group 4 semiconductor, like a zinc selenide, HCDT, zinc oxide, and zinc sulfide. So they are also semiconductor material. For the group 4, we know it's silicon and silicon germanium. For the group 3-5, this is what we know about, gallium arsenide, aluminum gallium arsenide. This is what like aluminum X gallium 1 X arsenide, something like this. So we also have the doping gas. Let me see. Do we have doping gas here? Well, there should be some gas for the doping. So now let's look at molecular beam epitaxy. This one is a very, very fancy name, but actually it is just a kind of evaporation. It is a physical evaporation process, but we need ultra high vacuum, so we need 10 to minus 10 torr. For the normal evaporation, we need a 10 to minus 6 torr pressure, but this one we need 10 to minus 10 torr to reduce impurity. So when we have this ultra high vacuum, we have very, very low impurity, because otherwise, if we have oxygen in the chamber, the oxygen can go to the film. So we need ultra high vacuum to reduce the oxygen and the nitrogen getting into the film. And we have separate heating to about maybe 800 degrees, for example, separate heating. So we need the high temperature to give single crystal epitaxial film. And we also have a in situ cleaning. That means before the deposition, we clean the substrate, we clean the wafer. This is needed for the epitaxial layer growth. So we can have the precise control of the chemical composition and the doping profiles. It has very low growth rate. For example, 1 hour, 1 micrometer per hour. This is much lower than evaporation. So evaporation, we can get 1 micrometer per minute if we want to run fast. So we have single crystal film with atomic layer precision. So here's the setup. You have the starting of the aluminum, arsenic, dopant, and gallium. So this is like each of them like a evaporation. But we have many elements coated, evaporated onto the substrate at the same time. So here, so the source here, so this one. So what is this one? This one is called a fusion cell. It's also called a Nathan cell. So if you don't remember what is the Nathan cell. So the Nathan cell. So we have this is the Nathan cell, something like this. So we have some material inside. For example, we have this gallium, and we have the vapor. So we have gallium vapor inside the box. Then the vapor will come out. The vapor will come out from this opening here. So we have a small opening. We have opening here. This is the Nathan cell. But this one is complicated. This one is more complicated. So you can see, so we have the crucible. So we have this crucible is here. So we have the crucible here. This is the crucible. So the vapor will come out. The vapor will come out like this. So we have the resistive heating. But actually, because this is very high vacuum. The very high vacuum. So the heating is done by the radiation. So the heating is done radiation from the resistively heated filament is by the radiation, because at the very high vacuum there is no thermal conductivity. The thermal conduction is very, very low. And also we have this radiation shield, and we have thermocouple. So we have very precise temperature control. This thermocouple controls the temperature to within 0.1 degree accuracy. So this controls the temperature, give you the feedback. So we have the closed loop feedback control to give 0.1 degree temperature control. But this is the Nathan cell. This one is much more expensive than the crucible. For the normal evaporator, we use crucible here. For the normal, this is like a carbon. This is for the normal evaporator. This will cost about $50. But for this nitrogen cell, like this, it costs about $50,000. So it's about 2 to 3 orders more expensive than a simple crucible. So it is for the evaporation, but much more complicated. So for the how can we get the so here we talk about we can have the precise atomic layer control. So how do we know we got atomic layer by layer? But this is done by the REACH. It's called reflection high energy electron diffraction. Reflection high energy electron diffraction. So we know about we also know about LEED. This is the low energy electron diffraction. This one is the high energy electron diffraction. This one is also used for the material characterization. I can show you. LEED. This is the low energy electron diffraction. LEED. So this is the spectrum. So what do you do here? So your electron shine on the sample, shoot on the sample. Then you look at the diffracted electrons. The diffracted electrons on the screen. This is the LEED. For the diffraction, so we have this Bragg law. So we have this. So this is called Bragg condition. This is Bragg's law. This is used for the accurate diffraction. But n lambda equal to 2D sin theta. So here we have the same thing. So we have n lambda equal 2D sin theta. So the difference from LEED, for the LEED, the theta is large. But for this one, for the refracted, for this one, the theta is only 1 or 2 degrees. So this is only theta is only 1 or 2 degrees. So this one is very small. You can see the sin theta is very small. So the lambda has to be also needs to be very, very small. So we know that lambda equal to, for the particle, lambda equals h over p. So h is the Planck. This is Planck constant. P is the momentum. H over mv equal to h over 2 me. So E equal to over 2 mv squared. So you can see, so the higher energy, the smaller the lambda. So now we need a small lambda. So we need a high energy to give you a small lambda. That's why I said high energy. This is why high energy, and it is reflection. So we shoot the electron beam onto the sample. The sample is here. Then we have diffracted the beam. Then we have this screen. We have this phosphor screen. So we can see the pattern on the screen. So when we have the constructively interferes, when the electrons interfere constructively, so we get the peak. We get those peaks. So we have the peak. So we can monitor the peak. For example, if we look at this peak here, this peak. So one of the peak. At this situation, we get high signal. So when we have 25%, we have 25% coverage, we get signal coming here. When we get 50% coverage like this, you know it's mostly random, we get the lowest signal. Then 75% we get coming here, and one monolayer full coverage. When we have the full coverage, we get to the peak again. Then this way we can count. So we can count the film layer by layer. As a result, MBE is the most precise deposition method, because we can count layer by layer a single crystal film, and it can be precisely controlled. But this one is also more expensive than the MOCVD. For the production MOCVD is better, but MBE is also used for the production, but the cost is higher. For the cheap thing, for example, the LED, light emitting diodes for the light bulb. LED light bulb, this one we need a low cost. We need low cost. So it is done by the MOCVD. But for the optical electronic devices used in the cell phone, optical electronic devices in the cell phone, sometimes we use MBE. So here at the University of Waterloo, we have Professor J. So I think maybe he has taught you, or maybe he will teach you some courses. So Professor J. Bick at in our campus, he has this MBE machine. This one is in the QNC. If you look at the QNC basement, there one of the lab is the MBE lab. Here's the photo of the MBE system, so you can take a look. Okay, thank you.